Welcome to the Walton Pi. Today we're going to be talking about power series. So a power series is an infinite series with increasing powers of x, or maybe a different variable like t or whatever variable you're dealing with. And those powers of x are parts of the terms of the series. So in other words, a power series looks like the sum from n equals 0 to infinity of some constant, so c sub n, times x to the n. So it might be like constant plus a different constant times x, plus a different constant times x squared, plus a different constant times x cubed, and so on. And it would do that all the way through infinity. Another general form might be where we have c sub n x minus a's to the n's, and this is going to be what's called the power series centered at a. So this is going to be the specific form of a power series that we're going to be using throughout the rest of this video, because it is the most generalized form. If we look at just c sub n x to the n, that's just an x minus 0. So when we are talking about a power series, I'm going to be referring to this, where it is a sum from n equals 0 to infinity of some c sub n times x minus a all raised to the n. So if we have a series, the next question that we probably would ask ourselves is where this series is going to converge. So unlike previous series that we've talked about, it is possible for a power series to converge at some values of x and diverge at other values of x. So the reason for this is x is a variable, so maybe suppose if x is 20, then that series might converge, but if x is 10, then the series might diverge. So depending on the value of x, we are going to get different results if we are testing for convergence or divergence. So if we have a power series, there are going to be three possibilities of where the series will converge. The first option is the series converges only when x is equal to a. The reason for this is if we plug in a for x, then we get the sum from n equals 0 to infinity of c sub n times 0 to the n. So we're going to take the convention that 0 to the 0 is 1, in which case this is just going to be c sub 0. And then c sub 1 times 0 to the 1, well that's 0. C sub 2 times 0 squared, that's also 0. And so what we are going to be left with is just c sub 0. So it'll converge to just the first constant. So that's one possibility. The next possibility is it's going to converge no matter what x value we put in. So we might have a series that converges everywhere, which is great. There are those sorts of series. And then the last one is that there is some r bigger than 0 where the series is going to converge if the absolute value of x minus a is less than r, and diverge if the absolute value of x minus a is greater than r. So this value of r is what's called the radius of convergence. You can think of it as it's the distance from a you can go before it stops converging. So in all of these, we also can think of the radius of convergence for the other cases. So if a series only converges when x is equal to a, we would say the radius is equal to 0. And if the series converges for all x, we would say the radius is equal to infinity. So we can figure out what the radius of convergence of a power series is. We can also use the root test, but most of the time you will see it with the ratio test. But I will go over briefly what the root test would be in case you ever need it. So if we're trying to figure out the radius of convergence using the ratio test, we can do that by looking at the limit as n goes to infinity of c sub n plus 1 times x minus a to the n plus 1 all over c sub n times x minus a to the n. You might notice that that is just the definition of the root test. You take the limit of your a sub n plus 1 term over your a sub n term, and you set that limit and you see, is that less than 1? If it's less than 1, then great. It's going to converge. So what it turns out to be is we can then just look at the limit as n goes to infinity of c sub n plus 1 over c sub n, because the x minus a's to the n plus 1 over x minus a to the n's, that just cancels out and is left with the absolute value of x minus a. And so that means we can then calculate just the limit as n goes to infinity of c sub n plus 1 over c sub n. So we can do this only looking at the constants. Whatever that limit is, that is going to be 1 over the radius of convergence. A very similar thing happens when we are doing the root test. So if we take the limit as n goes to infinity of the nth root of a sub n, well, in this case, that's just going to be the limit as n goes to infinity of the nth root of the absolute value of c sub n x minus a to the n. What that turns out to be is that's just the limit as n goes to infinity of the nth root of the absolute value of c sub n times the absolute value of x minus a. So the limit as n goes to infinity of the nth root of the absolute value of c sub n, that is going to be 1 over r in this case. So that's how we can figure out the radius of convergence using either the ratio test or the root test. Once we know the radius of convergence, we can then try and figure out what the interval of convergence is. So that's just going to be the set of all values of x, or whatever your variable is, where the series is going to converge. So we know for a fact it's going to converge from a minus r to a plus r. The question is what happens about the endpoints. So we have 4 different possibilities. The first option is it diverges at both endpoints. Then we have 2 options where it'll converge at one endpoint and diverge at the other. And then the last converge at both endpoints. So in order to figure those out, we need to test the convergence of each endpoint. So we need to test the endpoint x equals a minus r and the endpoint x equals a plus r. If we were to test x equals a minus r, we would test the convergence of the series c sub n x minus a to the n. We would then plug in x, so we get a minus r minus a all to the n. So that means we would be testing the convergence of the sum from n equals 0 to infinity of c sub n times negative r to the n. So however we would test that, feel free to use any of the other methods that we've covered. We just have to figure out, does that series converge? If we were to test x equals a plus r, we would have a very similar series, but we would just be testing the series from n equals 0 to infinity of c sub n r to the n. So that would be how we would test the endpoints. If it converges at one of those endpoints, you include it on the interval. If it diverges at the endpoint, you do not include it on the interval. We can also think of a power series as a function, where we say f of x is equal to that series, is going to be differentiable on the interval a minus r to a plus r. Note that this does not include the endpoints, even if the power series converges on that interval. We are only going to be looking at the open interval because derivatives require open intervals. So that is going to be how we are going to leave it. It has to be the open intervals. And then we can also take derivatives and integrals of f of x, and we can do those component-wise. So that means that if we were to look at f of x equals the sum from n equals 0 to infinity of c sub n times x minus a to the n, then the derivative of f is the derivative of that series, and we can actually move the derivatives inside the series. So we can look at the sum of the derivative of c sub n x minus a to the n, which turns out to be the sum from n equals 1 to infinity of n times c sub n times x minus a to the n minus 1. We can also take the integrals, so the integral of f of x is going to be the integrals component-wise. So, and I apologize for the typo on the last sum there, the sum from n equals 0 to infinity of c sub n x minus a to the n plus 1 all over n plus 1 plus c. That is going to be what the integral of our function would be. And both of those are going to be defined on the interval a minus r to a plus r. If our function f of x can be written as a power series, then we can actually figure out the coefficients c sub n. So our nth coefficient is going to be the nth derivative of f evaluated at a divided by n factorial. So f to the n, that's the nth power of f. F to the parenthesis n, that is how we write the nth derivative. So f exponent parenthesis 3 close parenthesis, that is not saying take f and cube it, that is saying find the third derivative of f. So we can write f of x as the sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. This then tells us what the Taylor series would be. So the Taylor series of a differentiable function f of x centered at a is the power series, the sum from n equals 0 to of the nth derivative of f evaluated at a divided by n factorial all times x minus a to the n. There's also what's called the Maclaurin series. That's just the Taylor series centered at 0. There's also a fairly useful inequality called Taylor's inequality that deals with Taylor series. So if our nth remainder, so r sub n, that's the remainder of how far we have to go to get our actual function after we've only done the nth partial sum. So our nth remainder is our function f of x minus the sum from k equals 0 to n of our kth derivative evaluated at a divided by k factorial times x minus a to the k. In other words, that's just all the terms after our nth term of our Taylor series approximation for f. We can then say if that's our remainder and the absolute value of f, our n plus 1th derivative of f at x is less than or equal to some value m for every x in some neighborhood distance d from a, then the nth remainder is going to be less than or equal to m divided by n plus 1 factorial times x minus a to the n plus 1, or m over n plus 1 factorial times d to the n plus 1. Now, we might be wondering, where could we use this? It turns out it's usually used if we are trying to prove that a certain Taylor series is the Taylor series representation of a function f. So if you're trying to prove a function is the Taylor series approximation for it, then you would use Taylor's inequality, or you could use it to estimate the error if you only added up the first several terms. But in general, that's not something that you're going to have to use on a daily basis. What is much more likely is using the Taylor series forms to find the Taylor series of a function, but not necessarily use the Taylor series, the Taylor series inequality. So the way that we would use it is if we can prove that the limit of the absolute value of r sub n of x as n goes to infinity is 0, that is how we would prove the power series used is in fact the Taylor series representation of f of x centered at a. So now that we've covered all of those, let's just talk about 7 useful Taylor series to know. So if f of x is 1 over 1 minus x, that is the sum from n equals 0 to infinity of x to the n, and this radius of convergence is 1. If we have e to the x, that's x to the n over n factorial, and that radius of convergence is infinity. If we have sine of x, that's negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. That one also has a radius of infinity. Cosine of x is similar to sine of x, except it's negative 1 to the n, x to the 2n over 2n factorial. Notice sine is 2n plus 1s, cosine is 2n's. One way you can remember that is cosine is even. It's an even function, so it's going to be 2n over 2n factorial. Sine of x is an odd function, so it's 2n plus 1 over 2n plus 1 factorial. So the next one is inverse tangent of x. That is negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Notice sine of x was 2n plus 1 factorial on the bottom. Inverse tangent is just 2n plus 1 on the bottom. And that one has a radius of convergence of 1. Natural log of 1 plus x is negative 1 to the n, x to the n over n, also with radius of convergence of 1. And our last one is 1 plus x to the k. That is the sum from n equals 0 to infinity of k choose n, x to the n. And that one has a radius of convergence of 1. I hope this video was helpful in understanding Taylor series, power series, Maclaurin series, and all of that fun stuff. Please check out some of my other videos, and please like and subscribe if you haven't already, so that I can continue to make these sorts of videos. Have a great rest of your day, and good luck with the rest of your math.